So, limit of multivariable calculus. So, today I want us to see something on limits. How can we relate limits as we saw earlier on? That was calculus 1 to limits in calculus 3. Okay, so without much ado, let's relate the two and let's see how we will go about it. Okay, so initially we have um, numerical method of finding the limits, and also we have the analytical method. Okay, so we will not focus on the numerical method, we will focus on the analytical method, because with the numerical method you'll be provided a table and you find out whether the limit exists or not. But with the analytical method we use paths. Okay, so directions along the path to determine whether the function really exists. That's the limit or not. Okay, so let's see. This is a few catch up I want us to do. So please just listen and listen carefully. With the first one, just I wrote the limit as x, the limit as x approaches a. That's from the left hand side of f of x is equal to the limits as x approaches a from the right hand side. That was positive. Okay, so this that I wrote, this is just from the calculus 1. Okay, so we can approach a function, or what this one means is that when we are approaching a point, we can approach it from the left, which is the negative side, or we can approach it from the positive side. Okay, so this is not part, but I just wrote it for us to understand it carefully. Okay, so let's go into the business. So with calculus, with multivariable calculus, for this we see we said a limit of f of x comma y approaches a comma b. Okay, so you know that x can approach a from the positive, or x can approach a from the negative hand side or from the left hand side. Okay, the same thing as y can also approach b from the right hand side or the positive, or the y can approach b from the negative or from the left hand side. Okay, so I also wrote, so it could be a limit of multivariable calculus, functions of multivariable calculus. It could be one or more points. Okay, so with this one, we have a comma b, but we can also have a comma b comma c. So that's the point. So this is 2 and this is 3. Okay, that's why we called it calculus of multiple variables. So we can have multiple or a lot of variables within our limit or within our function. Okay, so let's see how to go about it. In fact, in solving limits, it is very tedious in calculus 3. Yes, as compared to calculus 1, because as with the calculus 1, you only find a limit by approaching to that particular point, or with that particular place that has been given to you from the x coordinate and from the y coordinate. But with the calculus 3, you can approach the point that has been given from infinite paths. Okay, so these are some of the suggested paths we need to know, and this is the main point or the main part we need to know in order for us to find our limit in multivariable calculus. Okay, so what I want us to know is one, the horizontal line through the point AB. Okay, so the AB is the point that will be given to us. Okay, or we can also call the horizontal line, which is the x-axis, or y is equal to 0. Okay, 2, the vertical line through a comma b, which is y-axis, or x is equal to 0. Or 3, any straight line through the point AB. And lastly, the quadratic path, Okay, so we have four parts. This is the main one. I'm not saying this is the exact one. We have another one, but this is the one that we mostly use in order for us to find the limits in multivariable functions, okay, or calculus. So let's see some of few examples and some diagrammatic or schematic presentation. So I just did this presentation to enlighten our ideas on how we can go about solving limits in calculus 3. Okay, so I just drew this cardinal point like you see this point is 0 0. So in order for me to get to 0 0, one might come from the positive hand side, one can also come from the negative hand side. Okay, so anywhere you want to start, you can start. Okay, so with the x-axis, someone can approach it from the left hand side, that's the negative part, and someone can approach it from the positive part. In all, we will approach 0. Okay, with the x-axis too, we can approach the 0 from the negative side, and we can also approach the point 0 0 here from the positive side. Okay, so I related this one. So this A is for the calculus 1. Okay, that's what we need to know, or that what we all know from calculus 1. If we are finding a limit of a function, we just approach it from the left or from the right, and if they are the same, it means the function exists. Okay, that, and it was only x and y coordinates. By looking at the B, we have a lot. You see, we have three three or more curves here, okay, or three or more paths in which we can approach the point that will be given. Okay, so with this, we can approach by the x coordinates, we can approach the 0 by the y coordinates, we can also approach the 0 by the gradient or the straight line through the origin. That's the y is equal to mx plus c. But because there's no intersection, the the c component is 0. That's why I've written y is equal to mx plus c. Okay, so whether we also know, we can see this green curve. That's the quadratic part. Okay, so as I said, we have the quadratic part and any straight line through the point. So this is the straight line through the point. It could be here or here, and this is the quadratic part. Okay, so in order for us to know that or to find that a limit exists, it need to meet all these conditions. Okay, all these conditions are supposed to meet. Okay, so let's see some example. Example 1, show that the limit exists or not. So this is the question. Okay, so as I have said earlier on, we can approach them by 1, horizontal part, 2, vertical part, 3. So we will try all the parts. Okay, we will try all the parts. So if they are the same or we get the same value for the limit, it means the limit exists. And if they are distinct or different, it means the limit does not exist. So with this one, x squared minus y squared over x squared plus y squared, as x y approaches 0, you know that the x is for this, the first one, which is 0, and the y2 is for the next one, which is 0. Okay, so let's quickly see. Okay, so with a schematic representation, see the we can approach the point which is the 0 0 that was given in the question from the negative or the positive hand side. So this is nothing. It is just a representation of how we can approach the point 0 0. Okay, so this is how you go about it. We will first find the y coordinate, and we see whether we get a function or a value, and we also find the x coordinate as I said earlier on. So we are trying all the paths to get into 0 0. So we can try from the horizontal part, we can also try from the vertical part, we will get 0 0. Okay, or because we will get to this point. Okay, so let's see whether with the x component, y is equal to 0. So this is how we will write it. So the limit of x comma y approaches 0 0, x square minus y square over x square plus y square. So this bar here shows that along y is equal to 0. So it shows that this function is along y is equal to. So that's how I've written y is equal to 0. Okay, so y is equal to 0 means we are finding it on the x-axis. We are approaching the point, this point from the x-axis. Okay, so we know that y is 0. So wherever we see y, we just substitute 0 there. So we are going to get s square over s square, and we are going to get 1. Okay, we are going to get 1. So that we are done with the x component. Then we also do for the y component. Okay, and we know that for y component x is equal to 0. So we find the limit of x comma y as it approaches 0 0, x square minus y square over x square plus y square along x is equal to 0. So that's the y axis, along the y axis. Yeah. Okay, so the same thing, wherever we see x, we just substitute 0 there. Okay, so this place will be 0 0. So to be out there, so you are going to get negative y square over y square. And you are going to get the limit of negative 1 as x comma y approaches 0, which is equal to negative 1. So comparing 1 and negative 1, they are not the same. Okay, they are not the same. So I can boldly say the limit does not exist. Okay, thank you very much.